Hello everyone, I am Dr. Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about solid state chemistry. So, I will discuss about introduction, types of solid, crystal structure, element of symmetry, Bragg's equation, allotropes of carbon, diamond and graphite, and fluidity. So, three phases of matter: gas, liquid, solid. We all know that. So, gas molecules, liquid molecule and solid molecule. So, what is solid? Definite shape, definite volume, highly incompressible, rigid, constituent particle held closely by strong intermolecular forces, fixed position of constituents. Types of solid: two types based upon atomic arrangement, binding energy, physical and chemical properties: crystalline and amorphous. What is crystalline solid? The building constituent arrange themselves in regular manner throughout the entire three-dimensional network. Existence of the crystalline lattice. A crystalline lattice is a solid figure which has a definite geometrical shape with flat faces and sharp edges. Incompressible orderly arranged unit, definite sharp melting point, anisotropy, definite geometry, give X-ray diffraction bands, for example sodium chloride and cesium chloride. Now, amorphous solid, derived from Greek word amorph, meaning shapeless, no regular but haphazard arrangement of atom or molecules, also considered as a non-crystalline solid or supercooled liquid. No sharp melting point, isotropic, no definite geometrical shape, do not give X-ray diffraction band, and example glass, rubber, plastics. Now, types of crystalline solid: ionic crystal, covalent crystal, molecular crystal and metallic crystal. What is properties of ionic crystal? Lattice point are occupied by positive and negative ion, hard and brittle, high melting point due to very strong electrostatic force of attraction, poor conductor of electricity in solid state but good in molten state. Packing of the sphere depends on presence of charge species present, difference in the size of the anion and cations, and two types, AB types and AB2 types. Covalent crystal. Lattice point are occupied by neutral atoms. Atoms are held together by covalent bond, hard solid, high melting point, poor conductor of electricity. Two common example, diamond and graphite. Molecular crystal. Lattice points are occupied by neutral molecules. The molecules are held together by van der Waals forces. Very soft solid, low melting point, poor conductor of electricity. Metallic crystal. Lattice points are occupied positive metal ions surrounded by a sea of mobile electrons, soft to very hard. Metals have high tensile strength, good conductors of electricity, malleable and ductile. Bonding electrons in metal remain delocalized over the entire crystal and high density. Law of symmetry. Plane of symmetry, center of symmetry and axis of symmetry. Element of symmetry in cubic crystal: rectangular plane of symmetry 3, diagonal plane of symmetry 6, axis of 4-fold symmetry 3, axis of 3-fold symmetry 4, axis of 2-fold symmetry 6, and center of symmetry 1. So, total symmetry element present in cubic crystal 23. Now, you can check plane of symmetry, axis of symmetry and axis of symmetry, like 2-fold axis of symmetry and center of symmetry. Now, types of cubic crystal: simple or primitive type, body centered, face centered and end face centered. So, simple or primitive type, you can see at the corner body centered cell at the body, and face centered cell FCC or end face centered cell. So, what is the difference between? You can see the here yellow only the end face, but here yellow all 6 faces. Now, number of atomic per unit cell in a cubical lattice. Simple cube cell, 1 atom per unit cell of Sc. Body center cell 2 atoms per unit cell of BCC. Face center cell 4 atoms per unit cell of FCC. In face center cell 2 atoms per unit cell. Now you can see the simple cube. Number of atoms per unit cell 8 into 1 by 8 is equal to 1. 1 by 8. Number of atoms per unit cell 8 into 1 by 8 is equal to 1. Simple cubic rearrangement. 52% of space is occupied by the atom. Example, polonium. Now body centered cubic lattice. You can see here 8 into 1 by 8 plus 1 into 1, 2. Here number of atoms per unit cell 2. Body centered cubic lattice look like this. Example, cesium chloride and cesium bromide. 68% of space is occupied by the atom. Now face centered cubic lattice, here 4. Now face centered cubic lattice, you can see the example, sodium chloride, sodium fluoride, potassium bromide, magnesium oxide. 74% of space is occupied by the atom. In face centered cubic lattice, atom present per unit cell is 2. So atomic radius of a cubic lattice. Now simple cubic cell R is equal to A by 2, face centered cubic cell R is equal to A by root 8, body centered cubic cell R is equal to root 3 by 4. So where A length of the cube. Now radius ratio rule. Relation between the radius, co-coordination number and structure arrangement of the molecules. So radius ratio is equal to radius of cation and radius of anion. Greater the radius ratio, larger the size of cation and hence the co-coordination number. Density Z star Ma divided by N star A cube, Ma mass number. So sodium Na means Avogadro, A side and length, Z number of atoms. Now number of structure analysis by radius ratio rules. If you have the ratio 0.1 to 0.15, linear, 1.5 to 2.2, trigonal planar, 2.2 to 4, tetrahedral, 4 to 7, octahedral, and 0.7 to 1 body centered cubic. That is very important information. You have the examples like this: cesium chloride, body center, sodium chloride, octahedral, zinc sulfide, tetrahedral, B2O3 trigonal planar, and hydrogen fluoride linear. Now Bravais lattice, unit cell parameter length ABC, angles alpha, beta, gamma, total crystal lattice 7, total Bravais lattice 40. So crystal system with unit cell parameter, you can see cubic, A is equal to B is equal to C, alpha is equal to beta is equal to gamma, 90 degree. So orthorhombic, tetragonal, monoclinic, triclinic, hexagonal, rhomboidal. Now example of different crystal system: cubic, orthorhombic, tetragonal, monoclinic, triclinic, hexagonal, rhomboidal. Check the example like calcium sulfate 2H2 belongs to monoclinic, PbI2 hexagonal. Like you can see the cubic lattice simple or primitive, body centered and face centered. So orthorhombic system simple, body centered, in centered and face centered. Tetragonal lattice simple and body centered. Monoclinic simple and in centered. Triclinic, you can see triclinic. Hexagonal lattice, you can see the hexagonal. Rhombohedral lattice. Now structure of important ionic compound: AB type sodium chloride, rock salt, cesium chloride and zinc sulfide. AB2 types CaF2 fluoride, titanium oxide, rutile and silicon dioxide. Structure of sodium chloride rock salt: FCC type, coordination number 66. Calculations of number of atom of sodium chloride cell 1, 3, sodium at A center 3 and sodium at body center 1. So unit cell content are 4 sodium chloride per unit, per each unit cell 4 sodium chloride units will be present. Now check the sodium chloride structure here. This is the cesium chloride, BCC type, coordination number 8 to 8, number of atom per unit cell 1. Structure of zinc sulfide, FCC type, coordination number 4:4. Calculation of number of atom per unit cell, total AC is equal to 80 into 1 by 8 plus 6 into 1 by half is equal to 4. So total zinc 4 and hence total zinc sulfide 4. Now structure of calcium fluoride, FCC type, coordination number H2 8 for cation, 4 for anion. So K2O structure, FCC, coordination number 4:8, 4 for cation and 8 for anion. Structure of important covalent compound, diamond and graphite, You can see the structure of diamond, FCC type, tetrahedral, CC bond length 1.3 angstrom, refractive index 2.4, height, dispersive power of light, non-conductor of electricity, 3D network, hardest substance ever known, used as abrasive. Now 3D structure of diamond, graphite, structure of graphite, one of the softest substance ever known, 2D hexagonal layer structure, CC bond 1.45 angstrom, interlayer distance 3.54 angstrom, sliding nature, sp2 hybridized with 1 electron left over, specific gravity 2.2, electrical conductor, metallic luster, used as a good lubricant. You can see the 2D structure of graphite. This is the structure of fluorine. So important point about the fluorine, discovered in 1985 as 60, consists of a spherical, ellipsoid or clinical arrangement of dozens of carbon atom, 3 type, spherical, also called buckyball, molecules of the year 1991 by Science magazine, cylindrical, carbon nanotube or bucky tubes, balloon. Now structure of fluorine, 60 carbon atom arranged in pentagon and hexagon, 7 angstrom in diameter, saucer ball shaped molecules with 26 member and 12 5-member ring. Each pentagon is surrounded by 5 hexagon. No two pentagon are adjacent. Each carbon is sp2 hybridized, used as a photoresistance in the preparation of superconductor, in optical device, in batteries as a charge carrier. So Bragg equation, you know the X-rative, you know the detector, when incident radiations, then reflection radiation. There is a formula of this 2D sin theta is equal to n lambda, or n lambda is equal to 2D sin theta.